again, folks, in 114. Today we're going to be covering section 12.5. I sound surprised there. I'm not sure. Now, here's the calendar, so I'll confirm. Monday, today is Monday, my older sister's birthday, June 28th. So we'll be covering section 12.5. All right. The packet is hefty today. Some of this you're not really responsible for, but I thought it would clarify a little bit, so I'm going to walk you through this diagram. Then this is not really, well, I kind of made this as a worksheet. I want to show you something when we get to this page in regard to the empirical rule. It's written on there. All right. It's about percentages of the data where it would lie. This is an overview of different frequency distributions. The one that is imperative to us really is the Gaussian or normal distribution, which you find here. Okay, there's a picture of it. Okay, and then you'll be asked as part of basically the meat and potatoes of this section is to convert from data sometimes all the way to a probability. All right. A lot of times they give you what would be derived from the data, namely the mean and a data point and a standard deviation. You'll be given something called a z-score, which is what the z stands for, but this is the formula that would calculate that. Basically, a z-score correlates to an area under the curve, which could be converted to a percentage, which could be a probability if you like. So that's the train of thought, right, for much of your work. This is a little review of anything that is an equation that involves percentages. This is the kind of thing that I normally would teach in maybe 113, but it's worth maybe just looking at really quickly. Any part of it that would really be important would probably be this part, the beginning. And here's some suggestions of how to calculate the area if you needed to. All right, basically there's a table, though it's kind of hard to see it because it's so tiny. There's a full blown up copy of this, but I just wanted to sort of give you an at a glance. You could use a formula and you could look up related area in tables. All right. Here's the actual table blown up in, this is in black and white because I'm being a cheapskate and I'm trying to spare my ink. But this is taken from your textbook. And it's 2 pages. Here's the other page. And then there's some examples we'll go through. Okay? So I believe that is it. Also, here's, I swiped some stuff from the textbook if you prefer that explanation. But it says the same thing that I would tell you. All right. With my own diagrams. Okay? Alright, so let's go through this. It's very hot today. So I hope I'm not... thank God there's no smell-o-vision, right?
My math teacher's reeking up the internet now.
What a terrible thought that is. Yeah, let me scoot this over and we'll get busy. Okay, this may or may not be necessary. I'll block out the light a little bit behind me. There's our canvas. So I'm going to minimize now, and let's take a look at this. Here is that diagram I gave you from the onset of chapter 12. Not to be redundant, although it is a good habit when teaching math. This is again the sort of the itinerary. 12.1, 12.2, 12.3 were these 2 sections, and 12.4 is what we left off with last week. So that was the last thing we did. We're going to be doing this types of frequency distribution graphs. This is section 12.5. This is where we're at, and then tomorrow the last thing will be discussing linear regression. Okay. Now, as for new diagrams, this is the one I mentioned. We're going to be talking about graphs, so it occurred to me, let's discuss for a moment how this all evolves. All right. In math is a purist kind of field. And by that I mean that math people don't really care about the practical application things, of math. All right, that would be great if something had a practical application, but it's really more anything and everything that is possible. Right? A physicist would be a person who would say, well, we have math to rely on. That's the structure, right? But we want to apply it to some specific situation. Right? That's a purpose for it. Anyhow, think of math world as being, right now it's just two-dimensional, right? So we have quadrant 1, quadrant 2, 3, and 4, right? A slightly slimmed down version of math world might be business economics world. You notice that when you've ever had graphs on standardized tests, right? They never look like math world. They don't look like two-dimensional coordinate plane, Cartesian coordinates, all right? They always look like something like this, all right? Essentially, that's taking the chunk of math world that is quadrant 1 and quadrant 1 only, where there's positive up this way and positive out this way, all right, of numbers, all right? In keeping with that idea, we are in the subject of statistics right now, which can be applied to business and economics, of course. And we've been dealing with frequency distribution. So I just threw together, the idea of a frequency distribution table. You get to see these a lot in my lab, right? We have in one column classes that stretch in the same width, and then some frequency of figures that potentially are in those classes. Now, if it's truly symmetrical, which would be great, then you'd see a frequency distribution histogram. All right, a histogram is basically the pile of blocks. All right, and there's no gaps in between them. One class is butted up against the next one. All right, so let's just look at this for a moment. In the class of 1 to 3, all right, there's I just made this up, but a frequency of 2, so the height of the blocks would be 2. All right, in the class of 8 to 11, all right, the frequency would be 6, so therefore the total height of the blocks would be 6 in this case, and so forth. All right. Now again, ideally, this distribution would be symmetrical and much smoother, so not so pixelated, if you will. All right, a nice smooth curve about the average. All right, the average being right down the center here, right along from here to here. All right. Okay. Here's what I mean by smooth. If you narrow the width, ideally you would have more data, but if you narrow the width of the classes, all right, then this would be a lot less blocky, all right? And in theory, you could have more classes if you really wanted to, all right? And if you had enough data, it would basically start to develop into this nice smooth curve rather than be pixelated, and there'd be an obvious gap here, all right? Notice that we would specify an average here by x bar, right? And if we do one more thing with it, right? If we take it and instead shift the entire diagram so that these two things align, that the average, the mean, is not just whatever it is unique to the problem, let's just say it's 6, all right? But the whole kit and caboodle is shifted over. It looks like, what is that? That ghost online. To me, it looks like a ghost. Is it Instagram? I forget exactly. All right. That the symbol for that. Anyhow, if these two things are aligned, the whole graph shifted over, then you would have a situation that basically looks like this. Again, a smooth curve rather than a very blocky one, and the average is right at 0 intentionally so. All right? That's where we're headed right now, all right? This ideal scenario. All right? Now with that in mind, let me show you something here. All right, there's this diagram next. Okay, if we have that situation, right, where we have this smooth curve, all right, that basically is bell-shaped, and it's symmetrical about the mean, meaning that if you cut this in half, it would be the mirror image on either side. And lastly, the mean, the median, and the mode, 3 of the 4 types of averages that we're familiar with, are all the same, all right? Then we would have something that is referred to as the Gaussian or normal distribution per se, and not just the histogram in general, all right? Now, as a side note, there's this idea about the Gaussian normal distribution, the empirical rule. And the empirical rule is pertaining to these percentages here, right? 99.7% of the data, right, given these conditions for the graph, right, bell curve symmetrical about the mean, and that the mean, the mode, and the median are all the same number, 99% of the data would fit basically within 3 standard deviations this way and 3 standard deviations this way, all right, which is nearly 100%. All right, you notice that this is approaching the horizontal axis here, and it's stretching and getting tinier and tinier into infinity. All right, getting closer and closer to 100%. All right. But theoretically never reaching it, because why? It can get closer and closer, stretch further and further out, all right, and be 99.9, 99.99, you know, and so forth. 95% of the data would fit within these limits, all right, within 2 standard deviations this way from the mean, and 2 standard deviations this way from the mean. That's still most of the data, right? But not quite as much, all right? 68% of the data would be within 1 standard deviation, so like this. Right. So I know there's a lot of lines here, but just to emphasize, this much of the data, according to the empirical rule, if we truly have something that conforms to normal distribution, which is, again, these conditions, all right, 68% of the data would fit from here to here. That's 1 standard deviation this way and 1 standard deviation this way. Now, bear in mind, the standard deviation would fluctuate depending upon whatever the data is, all right? All right. Anyhow, if this is 68% total, all right, you can conclude that half of that would be on either side of this line down the center, right? So what's half of 68? 34, right? 34% would be here, and another 34% of the data would be here. Okay? All right. Now, what is this? How is this practical to us? Take a look at this diagram for a moment. Where is that picture? What you'll be asked to do is to calculate an area. All right. So let me show you this train of thought. All right. You can calculate an area by using tables, basically. The tables, again, are, if you look in your textbook, and you have these copies you could print from Canvas, it takes up 2 pages. That's how much data we have. But we're grateful for it because the tables will simplify our lives. We don't need to perform any sort of calculus to calculate the area under a curve. I mean, that would be cool, all right? But it isn't necessary because we have tables to look up, all right? This is, again, the train of thought. You have data values, which are represented by X. You have a mean, which is represented by X bar, and you have a standard deviation, which could be given to you or you could calculate from scratch if you really needed to.
How so?
Rather than use the formula, which could be a little tedious at this point in the conversation, you would use your calculator to get you the standard deviation. All right, you'd have to input the data, right, if it isn't given to you. That will create something called a z-score, which, as you can see, right, a z-score is a glorified fraction, right? There's the top and there's the bottom, right? Essentially, it's a ratio, right, of the average distance, the distance from the average to the individual data point, right, divided by the standard deviation. So you have a ratio, a certain fraction of the standard deviation, right? This is proportionate to basically an amount of area that would be under the curve, right? Which again, you look up the area in the table. Whatever the z-score is, right, whether it's given to you or you calculate it, you look it up in a table, right, rather than perform calculus, right? Now, this will be given to you as a decimal, right? But the decimal, if necessary, you could convert to a percentage, right? And I alluded to that here, right? Now, you could also regard it as a probability since it's a percentage, right? That's the next step if you were going to go that far in the train of thought, right? To remind you a little bit about percentages, I made this diagram. This is the kind of thing, again, you would see in maybe MAT-114. I drew it at the time when I first taught it. This I've finally gotten around to making a formal diagram. As a person who will teach, maybe elementary school kids or kids in middle school, all right, keep this, and if you find it useful, spread it around, all right? There's basically three types of percent equations. That is, equations that involve percentage somehow. All right. In this case, there is the part equation, is usually how it's referred to, or the base equation. You're looking for a different part of the equation, but it's called base. Or you're looking for the actual percentage itself, right? And you can kind of tell visually by this situation. If you just see these words in context, what is such and such, or is what, the operative term in tandem here is, and then the phrase what in English, right? If you see that, you're probably looking for the part, which is basically a piece of the whole. If you're looking for the base specifically, that's usually the original amount of something. That is the whole. All right, amount of something. All right. You can tell usually that is the thing that you're looking for by the phrase of what, right, rather than is what. English is confusing, all right, but you could pretty much rely on that, all right? If you know that you're dealing with percent equations, that is something that involves a percent somehow, when you see of what or is what, that means probably looking for this, probably looking for this, all right? Percent is even more straightforward because it will say simply what percent, Now, in terms of the math involved, all right, if you're looking for a part, that is a piece of the whole, a portion, all right, it's just purely arithmetic. It's just one thing times something else, all right? If you're looking for either of these things, the base, that is the original amount, or the actual percentage, you're going to end up dividing two things. If you have a percent, you're going to end up dividing and then multiplying by 100 for the sake of presentation, for putting it in the style of a percentage. That means you're going to get a decimal, and then you multiply by 100 to move a decimal point twice. All right. Now, here are three examples. They're not too difficult because I'm not that creative. All right. But this is a good way to teach a kid how to translate most simple word problems. Right. 50% of 20 is what? The word of translates to multiplication. Let me blow this up just a wee bit. Get rid of some of the gobbledygook here. The word of translates to multiplication, The word is translates to the symbol equal. So the cool thing about that is once you teach a kid that, it's very empowering. They will go, oh, then everything around it sits here and here, right? Yep. All right, so if you see a 20, then you just plop a 20 in between. And if you see a 50% here, you could write this in the style of a fraction, or you could write it alternatively in the style of a decimal. But in either case, what are you doing? You're just simply multiplying. This is just arithmetic. It's not lying to you. It is what it is. So 50% is a half, right? A half of 20 is what, intuitively? 10. Right? And that would be the end result. Right? That's really the level of sophistication, here in our subject today. All right, if you had to find a probability, all right, you're converting a decimal to a percentage. How so? By multiplying by 100, or without thinking, moving a decimal place twice. All right, just to complete this thought, if you're looking for a base, all right, of is still times, and is still equal. But the question of what is missing is now in between. So I'm just going to put a capital B here for base, right? And I'll put the 50% in the style of a decimal because it's easier, all right? And a 10 would be seated here. Now, this is the way you would translate it from what is verbal to what is symbolic, all right, directly. But what you end up doing is you're performing algebra because of the nature of the missing piece being in the middle here. So you would divide by 0.5 here to move it and cancel, and divide by 0.5 here to balance, right, this side of your equation. All right, and then whether you use your calculator or what have you, your own wits, 10 divided by 0.5, all right, it would end up being 20, all right. All right, here's how so. You can always draw a division box here, put the 10 inside, move 2 spaces, 0, 0. 50 goes into 100 twice exactly, and it ends up being 20. Right. Again, I wasn't too creative when I created these. I just wanted to demystify it. All right, last one here. All right, what if you're looking for the actual percentage itself? Again, start with the translations. It's always a good exercise for kids. All right, of is times is equals. That means that the 20 sitting here is where it's supposed to be, and now this 10 is still here. But if you're looking for a percentage, let's just substitute a p here, right? Because the thing that you're multiplying by is a variable, you really do have to employ algebra at this point once again. Right? There's an added step though for the sake of presentation. The opposite of multiplying by 20 is to divide by 20. And if you divide by 20 here, you're obligated to divide by 20 here for the sake of balancing. Okay, so what are you left with? You're left with 10 over 20. Pull some tricks, mental math, right? Pair of zeros goes away, you have a half. If you're going to convert a half to a decimal, it's the same as if you divided 1.00 by 2, right? Or you could put 10 there and use 20 instead. 2 doesn't go into 1, it's too small, all right? But 2 goes into 20 exactly 0.5 times, all right? Now again, that's a decimal, not a percentage, which is what you're required. So for presentation purposes, you perform the added step of multiplying by 100, and the effect is that this decimal moves twice. So you end up with 50%. Okay? That's just a review of the old stuff. All right? Realistically, it is really just this that you'll be employing at all in section 12.5. All right, converting, taking a percent of the data, whatever the number is, all right, and multiplying it by that percentage, right, in the style of a fraction, in the style of a decimal. All right, now, insofar as graphs are concerned, let's see where normal curve or Gaussian distribution fits in the big picture. All right, here is, again, to summarize, different types of frequency distributions, because there's several, right? At least these, and how to distinguish them. It's very hot today. Pardon me 1 moment. Look at this. Okay. All right. To give you a little information for each of these, all right, for reference, you don't really have to worry too much. This is the one that's really the most important to us, in which the empirical rule would apply. All right, you'll do a lot of problems in section 12.5 for this, and also for 12.6. All right, but what if you had a rectangular frequency distribution? It would look something like this. I stole this from your book. All right, this is a situation in which all frequencies occur in about the same amount. All right. What's a scenario that would simulate that condition? All right. Die roll. All right. If you roll a die enough times, all right, you will see an equal number of 1s, an equal number of 2s as a roll, an equal number of 3s as a roll, 4s, 5s, and 6s, right? Because that's how many sides of a die there are. Right? I had some dies. Where did I put them? How did I lose them? I know I didn't throw them out. Oh, here they are. It's a little crazy. Here's a cheesy dice I made, a die, right? A 6-sided cube, right? If it's a truly fair die, it will just, any one of these sides is equally likely, right? In terms of frequency, though, that's the way that the histogram would basically look, all right? That given enough rolls, all right, they'll occur, each one of these sides, whatever number they are, in the same amount. Now, if you get a situation like this, in which you have a shape, it's called J-shaped, all right? To me, it's made easy to remember as stairways, up or down, all right? This is when your frequency is increasing, or frequency decreases. Right. Frequency is headed down, as you can see, from left to right. In this instance, frequency is increasing from left to right. You always read from left to right. What's the situation that would simulate this? Perhaps a study of hours of study per week, or in a week. There are some of us in academia, right, that it's hard to get going on Monday, like today, right? So you're like, frick this, put in an hour, maybe that. But as you get used to being, in the condition of being in school or what have you, your job, maybe you put in more hours so that you're free for the weekend, So as the week progresses, you put in more and more to spare yourself trouble on the weekend, right? Or maybe the opposite is true, all right? Maybe you're raring to go on Monday, right? I'm like, oh yeah, I'm gonna be best teacher or professor ever. And you put in so many hours on Monday, and as the week goes on, you get more and more disheartened, and you're like, frick this, I don't want to do it anymore. Not to corrupt you one way or the other, but as you can see, there's it's not symmetrical as a bell curve would be. It just either increases or decreases, according to some study of frequency. Right. Then there's this situation. We have a bimodal histogram of frequency distribution. This is what you would call two non-adjacent, meaning not immediately next to, not necessarily equal, frequencies. That are distinguished. Easily distinguished. Not to be crass, is that the word? But this is a funny way to remember it, really. If it looks something like a middle finger, this is like getting two middle fingers, right? Yay. What would be a scenario that simulates this? If you had some data about the weight of men and women, right, on the same diagram, frequency distribution of a population of men and women, and these might be the average of ladies, perhaps, just ever so slightly a little bit lower. And this might be the frequency, the average of weight of men, right, which is maybe a little bit higher, right. For men and women that are the same size, you should really expect them to weigh about the same, right. Dudes tend to be taller, but not exclusively. Right, that would account for the only real distinction there. Right. Anyhow, that's a situation we have two non-adjacent, they're not next to each other, because if they were next to each other, they'd be a little bit more like this, right, so that they're distinguished. You could also, instead of calling it two middle fingers, which is, I guess a low class of me, it looks like a skyline of a city, but they're easily distinguished. Notice another thing too, although it's called bimodal, which would imply that there's two modes here, all right, and there are. All right, remember when you have something that's bimodal, the only thing that is the same is the frequency amount, all right, but they don't necessarily have to be equal amounts. That is equal, they don't have to be equal frequencies, all right, to be considered bimodal in terms of a graph, all right. This one is a little bit shorter, notice, than that one. All right. Then there's this skewed data, all right, or skewed histograms. All right. There is a distortion, basically, in a situation like this. I'll make it red just to make it a little bit different. A distortion likely caused by an outlier. Remember, an outlier is a suspiciously small or large piece of data that's pulling the graph one way or another. That would be otherwise good data, except for maybe that dud of a piece of information. All right. Now, in this situation, if you have what is called tail left, that's why I called them devil tails, because they'd be deviling, right? There's a little point here. The outlier perhaps is pulling the diagram towards the skewing left, you would say, because it's tail left, right? If you have a high piece of data that is an outlier, perhaps, then it would be skewed right, or you might call it tail right. All right. In terms of the mean, median, and mode, all right, as I alluded to before, that's the ideal situation that they're all aligned. All right. When you have skewed data one way or the other, right, what would happen is that the mean would be stretched towards the left as well. The median would be in the middle, or between, I should say, median. And the mode would be on the other end, right, when this occurs, right? Rather than them all aligning, sorry, this is going to sleep now. the mean, median, and mode would be in relation like this. The median would be the low figure. Pardon me, the mean would be the low figure. The median would still be in the middle of these three. And the mode would be a little bit more towards the right. When you have this situation, it's reversed. The mode would be on the low end. The median would be in the middle still, but the mean, which I'm going to use X bar here because I'm running out of space, would be on the high end. When you have tail right or skew right data. In the packet, I left it because I liked it. There's basically a diagram to summarize that, so I'll point to it here. If you dig through the copies, this is essentially the same thing. Skewed tail right. The mode is on the low end. The median is still in the middle, but the mean would be stretched in the direction of the outlier. If it's skewed left, I'm reading it backwards, I'm sorry. Then the mean would be on the high end, would be on the low end. Median is still in the middle, and the mode would be here. They're not aligned when you have skewed data. Is the real point. Now this is a little redundant, but again, just to make sure, a couple of my bases here. Let's look at the situation in the center here. Again, the ideal situation, the normal or Gaussian mountain, if you will, conforms to the empirical rule. And that is pertaining to the percentages of the data again, 99.7, 95, and 68% respectively. If something is truly a normal distribution, it would be symmetrical about the mean. And in fact, the mean, the median, and the mode would all be in the center. They would align in a situation like that. They would not be skewed as they are over here. Okay? All right. Let's see. Now let me show you one last thing, and then we'll finally do some examples. Often you'll be asked to calculate an area. If you have to calculate a z-score, which is pertaining to this formula here, then you could just use the formula. You'd have to be given the parts of the formula. But if you have to calculate an area under the curve to figure out a percentage of the data, then there's some tricks to that. So you're going to find a z-score one way or another, but the worst case scenario, you'll be given the average and a piece of data. Hopefully a standard deviation. You have those, you can calculate it. For areas that originate from the left, which is that's more or less the normal situation, the usual. You read from left to right. And it's fairly straightforward. What you're going to do is you're either going to be given the z-score, some decimal number that I would purposely label here every time. And then look up what that z-score appears in this data table that is available. All right. So let me just zoom in on that, if I may. I believe that is in this bunch of diagrams here. Yeah. All right. It's in color, thankfully. Let me hide the thumbnails. It's like 95 today. I'm dying. If you had a figure like, let's just say, 1.68. Suppose you had a z-score that was 1.68, right? There's two tables, one that is basically the positive numbers and one that is the negative numbers. So if you scroll up here, you'll see that there are some negatives, right? If you were to look up the number 1.68, you would have to go to, let me zoom in just a wee bit. You would have to go to the row heading that is 1.6 firstly, and then realize that this is this first figure that is here. This is the column heading of, I'll show you by scrolling up a wee bit, of 0.00. So this would basically be 0.60, this would be 0.61, 0.62, 0.63, 0.64, and so forth, right? It's basically showing you the precision for the hundredth place, okay, on the column headings, okay? So here's this first figure. Let me get this out of the way, sorry. 1.68. All right, you go to the row heading 1.6. This is understood as being the area for the value of 1.60. All right. If that's 0, then this is 1, 2, 3, 4, 5, 6, 7, 8. You would need to go here. This would be the area for z-score of 1.68. And notice that it is a decimal number, right? Because it's proportionate to an area of one whole. So if you're 0.9, you're very, very close to being the entirety of an area without being the entirety of an area, right? Because 1.000 would be the total area. Okay? So we're going to be using a table like this a lot, right? And don't let it intimidate you. It's there for practical usage. Okay? Just know that the column headings are 2 zeros, 0, 1, 0, 2, 0, 3. That would be 0, 9. Right? So if you're at 1.6, this is 1.68's area. Okay? All right, now going back to that other diagram, let's say hypothetically, you had a slightly more complicated situation where you had an area that was between z-scores. If you have an area that is between z-scores, you're still going to rely on the data table, all right? But what you're going to do is imagine this situation. You're going to imagine firstly, and I'll use colors to emphasize this, that you have a larger area, which I'm just going to make red, all right, that stretches all the way from the far left here up to the red line, all right? And you'll figure out, well, what's the area for that according to the table? Point whatever it is, 0.87 or what have you, all right, or something like that, all right? And then from that larger area left to right, you will subtract out a smaller, I'm just calling it blue area to distinguish it, all right, which would not go nearly as far. It would go from here and overlap up to that point, right? If you subtract the smaller area from the larger area, you get the area between, right? Because they only overlap up to a certain point, right? If you basically take out that bit of it that is overlapping, then what is left is just this area that is between, right? Via subtraction. Right? If you have a situation where you have a graph that has an area that seems to be originating from the right instead. So you have this situation. There's two things that you can do. You could take into consideration that, well, the total area from left to right, that is this whole kit and caboodle, the total area would have to be equal to 1.000. Remember, it's proportionate to an area, not a specific area. All right? that is like, so many square meters or whatever. They don't do that. It's just a decimal equivalent, right? And that's sufficient, all right? If the whole kit and caboodle is one whole, right, then what you can do is figure out the area from the left that would be the area that goes up to just that far. Basically the area that goes just up to this line where you're looking. Even though that's not the area you want the area beyond it. You could calculate the area from the left, from here to here, up to that barrier, and then do a similar thing. You're going to subtract, but you're going to subtract it from one whole rather than some other area. Right? And that will give you what should in theory be left over. All right? If you subtract a chunk out of the total, you're going to be left with the smaller chunk in theory. All right? An alternative, and this is arguably more efficient, is just to pretend that you have an opposite sign z-score. In other words, you can take advantage of symmetry, because ideally we're doing this for something that is symmetrical to begin with, right? And look up the opposite sign z-score, and it will give you the same answer without having to do any subtraction. Just flip the sign of the z-score and look it up in the table. All right? That's kind of cool, right? And certainly more efficient. All right? I would nonetheless, always tell somebody the alternatives, let them choose. All right, which way they want to do it. It's better to engage in mental flexibility. All right, finally, let's do some examples now. So if you look at basically this sheet, do a couple of these problems. Where did I put that? Oh boy. My pages are sticking together because of the humidity. Let's take a look at a couple of these. All right, get your feet wet. Maybe I'll zoom in on this now. Applying the empirical rule, let's start with this. The heights for females that are the same age are normally distributed, right? Whenever you get that phrase thrown at you, normally distributed, automatically draw a picture that just looks like a little ghost, like that. Draw the bell curve, okay? In a random sample of 500 females, all right? This would be 500 females total. All right. Determine the approximate number of females in the sample who are expected to have a height within one standard deviation of the mean. Now, according to what's one standard deviation? Remember that you can have a standard deviation 1 this way, 2 this way, 3 this way, usually. Negative, negative, negative. Or 1 this way, positive, 2 positive, 3 positive. Within one standard deviation is, according to the empirical rule, a person who has a height somewhere from here to here. Right? So according to the empirical rule, what percentage is that? It says within one standard deviation, that's 68% of the data. But in this unique situation, it's how many people total. How many ladies? All right, 500. So what you'd be calculating in this case is, all right, the approximate number of females who are within this space, right? Area, I should say, right? That's asking you 500, pardon me, what is 68% of 500? All right, remember it's a part equation. So it'd be 0.68 times 500. Do that really quickly. There's your calculator. 0.68 times 500. And you see that it's 340 females. Right. This would be equal to 340, right? With nothing else than the empirical rule, which I spelled incorrectly. Empirical. Empirical. Sorry. Within 2 standard deviations of the mean, right? Again, according to the empirical rule, which applies to normally distributed data, all right, it would be a little bit further out. 2 standard deviations would be from this line up to the mean this way and to this line out here, all right? So more data. How much more? 95% of the data. So if we're talking about 500 people, 95% according to the empirical rule of 500 would be what? 0.95 times 500. I should have put a decimal there. Clear. 0.95 times 500. 475, right? 475. Okay. So there's nothing to that, all right? Just realize it's a percentage times the total amount. That makes it a part equation, right? So it's really just arithmetic, this times this, but just put it in the decimal form. It's probably the easiest thing. Okay. The next part, as you can see, is actually calculating z-scores. So let me scoot this up a wee bit here. Find z-scores, all right? A normal distribution, again, this phrase, you see this, all right? Get in the habit of automatically drawing this little ghost. All right. X. Because that's what it's implying, all right? Has a mean of 60. All right. So that means that a 60 would be here in theory, all right? And a standard deviation of 60 and a standard deviation of 15, all right? Determine the z-scores for the following data values. Remember, we have this formula, x minus the average over the standard deviation. You have all the information you need, you just have to do the calculation, all right, in the correct order of operations. Now, because you have 2 things on top here, you have to simplify by subtracting first, and then dividing by the standard deviation as an afterthought, all right? When you have rational expressions like that, you sort of defy order of operations, not really, all right? But input these numbers, and you'll do the calculation 4 times. So, in this instance, if I borrow this formula and these 2 figures, all right, I don't have a lot of space, so what I'll try to do is I'll confine myself ahead of time. Here's A, B, C, and D. This is a dud of a blue mark, of course. This is the data value X, data value 81, data value 60, data value 33. Right? So to calculate the z-score, it would be essentially 75 minus 60 divided by 15. What is the difference between 75 and 60? Just 15 itself, right? So what is 15 out of 15? All right, 1 whole. This is z is equal to 1.00. Right? I'm just using 2 decimal places, that is to the hundredths place, because that's the precision of the table usually if you were going to look it up. Okay. 1 is sufficient if you like. Next one, it's going to be 81 minus 60 over 15 again. All right. What is the difference between 81 and 60? I would say it's what, 21 over 15? 21 over 15 is something you could use your calculator to get the decimal equivalent, or try to whittle it down. Let me do that really quickly. Let us say these are both divisible by 3, because they are, and that is 7 over 5. All right, how many 5s can you squeeze into 7? 1, with 2 left over, so it'd be 1.4. Okay. Next one, 60 itself. If you had 60 minus 60 over 15, you're going to get 0 over 15, which is just equal to 0, of course. And then the last one is 33, right? 33 minus 60 over 15. 7 would be 40, and it would be 27, right? Because of the nature of this arrangement, remember that you would have a negative in this case. Right? You'd have something that you could still simplify if you want to pull tricks. They're both divisible by 3, as they should be. So that'd be negative 9 over 5, right? How many 5s can you squeeze into 9? 1, with 4 left over, which would be 8. And it would be negative 1.8. Z is equal to 1.8. Z is equal to 0. Z is equal to 1.4. Right? And Z is equal to 1. And 1.0 if you like. Now, what does that mean? All right? It basically means that the data, if you have a z-score of 1, it's a positive 1. Right? This is implying data is above the mean. This is still also the same thing. Data is above the mean. 0, if you have this implies that the data value is the mean, right? Because it was 60, right? And we already been told that it was 60. Yeah. If it's negative, that means that the data value is below the mean. Now another thing, that is what the sign really and the 0 is indicating. If you have the z is equal to 1, there's some other implication there. That means that your data value is 1 standard deviation up, right? Because it's 1 exactly, right? If it's 1.4, it would be 1.4 standard deviations, right? No standard deviations because it is the mean. This is technically negative 1.8 back, right? Standard deviations. Right. As z-score indicates where the data value is in terms of the standard deviation. All right, it's either above or below, right, the mean. Now let's do some area problems. Sorry for the mess. Determine the area under the curve. All right, in this case, you are given the z-score, because this is just an exercise in how well you can look up the table. But what I would encourage you to do is since they're discussing a normal curve, again, get in the habit every time with drawing a very simple picture and labeling it. That'll get you a little bit more cozy with it. Alright? Horizontal line, horizontal line. And here's a bell curve. Little ghost diagram. Sorry, it's a little sloppy. And label it. Now, if it's a truly normal distribution, then this average would be 0. Alright? It's aligned, it's scooted over to such an extent that it's aligned with 0. So, alright, if you're given a negative number, where is that in relation to 0? Alright? It would be over here. Right? This would be -1. So that means that you're, again, when you're reading left to right, this pertains to an area that would go only this far. Alright, this is a z -1. If you have, as in this case, a positive 1.19, again, in relation to x bar equaling 0, where would a positive number be in relation to 0? To the right of it. So just sort of draw a simple line here and label it positive 1.19, and then we're referring to this much area. So you would expect a larger area, basically. Although, you know what, let me correct myself. This says to the left is correct. In this situation, it looks suspiciously the same, right? But it's saying, what is the area to the right of z? It's the same location here. This is x bar is equal to 0. Positive 1.19, but it's to the right. So we're really just referring to this area that occurs after it rather than before it. And in the case of this one, it's between 2. So you have a negative number and you have a positive number. If again, down the center, x is 0, always, right, when you draw these, all right, then this is negative 1.62 here, and this is positive 2.57 would be over here somewhere. It doesn't have to be perfect, it just has to be in relation to 0. All right, now this is again between. So we're referring to this area between these two lines, this barrier and this barrier. All right. From the left, just a little bit. From the left, a lot. From the right, technically, and between areas. And what we need to do is to take these z-scores, since we didn't have to calculate, and maybe pull a little bit of trick. These two, this one that is A and this one that is B, is going to be completely straightforward looking at the diagram. So if you see -1, go to the diagram here and go to this table, and we'll look at the negatives here. Let's look, maybe, I hope it's not too difficult to see. Let me see. Okay, just come on, cooperate. There you go. We're going to go to, I'm kind of, go down just a little bit. We're going to go to the column, the row heading of -1 for z-score. All right, and since there isn't anything else, it's just -1.00. That's the very first thing that we're going to look at. This is the area that pertains to that. The area would be 0.1587. All right. Think of that as being about 16% of the total. Whatever the total is. All right, I'm just rounding, hypothetically. All right. If you had a situation like this where you have a positive figure, again, you're going to go to the part of the diagram where you see positives, and now you have to read 2 decimal places, so the hundredths place. go to 1.1, and real is 1.1, right? Now we need to go to the precision of the hundredths place. So this would be 1.10, 1.11, 1.12, 13, 14, 5, 6, 7, 8, 9. And in this situation, the area would be equal to 0.8830, which would be, approximately 88% of the total area. Okay? Now, for this situation where you have the oddball where the data, the question is from the right, you could again do the slightly more sophisticated thing, which is, where is this? As I mentioned earlier, you could figure, all right, well, the total would be one whole. So I could figure out what the area would be up to that point, and I just got it. It's 0.8830. All right. So here it would be, the area would be equal to 1 minus 0.8830. Or you could just simply pretend that this is negative 1.19 and look up negative 1.19 instead, because it would be the symmetrical amount. All right. So let's do that. All right. I'll do it both ways, but let's see. Negative 1.1, and we'd have to go all the way to the edge here to be negative 1.19. So the difference of 1 minus 0.8830 should be that amount, 1.1170. Let's just verify with the calculation now, right? 1 minus 0.8830. And there you see it, right? 0.117, 0.1170 for the precision, all right? Do it either way, all right? Just realize, again, as ultimately, you have more than one means of getting from here to there, okay? Let's see. All right, I'm standing in the front too much. Let me get out of the way here and do this. All right, now we're going to go back and do the one between, as I mentioned. All right, so we have to calculate, this is when you have between problems, it's always the more complicated type, all right? But it isn't really difficult because it's a strategy you will employ 100% of the time, which is to subtract area that far from area just this far, okay? So you're going to look up two things in the table, the area pertaining to this and the area pertaining to this, and then subtracting them. All right. So area, large area minus small area, if you will. All right. Let's look up the positive first, because that should be the large area. So go back here. 2.5 in the column, the row heading. So we have, this is 0, 1, 2, 3, 4, 5, 6, 7. 0.9949. 0.9949. Because it comes from here. Okay. Now we need to go to the other table, look for negative 1.62. Let me get it out of the way of the camera here. Negative 1.6, that's 0, 1, 2 hundredths. So we're going to subtract 0.0526. Pardon me, 5. 2.6, yeah. Okay. And that will give you the area between. Okay. So, I'm sorry for all the distractions in between here. I try not to superimpose too much. There we go. We have all the information. So 0.9949 minus 0.0526. All right, and you end up with that 0.94. It's like 5.3, so it's 2.3. So backwards. Okay. 9.423. That means, about 94% of the total area. If you're going to round the percentage, right? You don't have to. Okay. All right, and this would be also the same thing. This would be about 12% of the total area. Moving on, let's look at example 4 here. Sorry. Look at 4, I gotta clean up my messing. Alright, we'll look at this. Alright, intelligence quotients, IQ scores are normally distributed with a mean of 100. It's calibrated that way. And the standard deviation of 15. Determine the percent of individuals with IQ scores under these conditions. Alright, again, if something is normally distributed, alright, start by drawing this diagram. A little ghost, alright? And the center average in this case is described as being mean of 100 instead of 0. All right. And a standard deviation of 15. All right, now, you're going to determine percentages in this case. So you're going to go the whole 9 yards, all right? Let me just refer you back to this train of thought. All right. We're going to probably have to employ this formula because we're quoted as having a mean and a standard deviation unique to this problem. So depending upon the data value, we're going to input it into this z-score formula. Then we're going to look up the area, and then we're going to calculate the area as a percentage. All right, so below 115, now, what does that mean in terms of the picture? If 100 is the dead center, all right, 115, the line would have to be right there, but below it is actually implying just from the left. So there's going to be a large percentage of individuals with IQ scores that are below 115. A number of people is really what it is, all right? But in the style of percent, all right? So here's the formula. I'm going to put it in green on purpose because green just doesn't write well. So I can draw on top of it. X minus X bar over standard deviation. All right. Unique to this specific thing, all right, we're going to put in 115 minus 100. We'll get a positive number as a result, and then we're going to divide by 15. All right. The difference of 115 and 100 is naturally 15. So let's see, 15 divided by 15 is positive 1, all right, for a z-score. All right. This is exactly 1 standard deviation above. All right. This point right here. All right, but we want everything back from that. All right. So we're going to look up 1 now in the area table. So 1 whole is here, which would be, although it's smudged slightly, 0.8413. This correlates to 0.8413. All right. Now, since that's a decimal, okay, 0.8413 in its style of a percentage, all right, is the same as just having to multiply by 100, and the effect is moving a decimal like so. So this is equal to 84.13% of people, individuals, in the context of this problem. All right. How many people have an IQ score of 115 or lower, which is what below 115 is saying? Most people. Right, greater than 50% by a lot, 84%, a little bit more than that. All right, what about below 70? In this instance, all right, you're going to start a little bit further back from 100, right? So this would be where the line is. 70 would be here, all right? And we'd be talking about an area of people, a percentage, that only goes that far, all right? We would again use the same formula for z-score. Z is equal to x minus x bar over sigma. That's lowercase sigma, I swear. All right, so a 70 minus 100, you're going to get a negative in this case, over 15. The difference of 70 and 100 is 30, negative 30, right? Over 15, which would be negative 2 in this case, right? Let's look up negative 2 exactly in the table. It's a little obscure, but right here, negative 2.0, so this would be 0.0228. And I'll put this in blue just to distinguish it. Right. This pertains to 0.0228. Okay. So if you have 0.0228, and again you're going to convert it to a percentage, that's the same as multiplying by 100, and the effect is to scoop the decimal over twice. So you have 2.28%, right? which is not a lot of people, right? Interestingly, if you had a person above, 115, it'd probably be a similar percentage of the population, right? Let's do 2 more of these and then move on. All right. If you were going to calculate people between 70 and 115, since we've already done those, right, that would be referring to, again, a larger area minus a smaller area, right? To address this question, this would be large area minus small area. Or larger or smaller. Alright, so we calculated for 115's area as 0.8413. And the smaller area we just got is 0.02 rather. 228, and we would subtract these. .8413 minus 0.0228 as 0.8185. In terms of a percentage, that's 81.85%. Would be just in here, between this line and this line, because of that difference. All right. All right. Let's do this one last one above 122.5, because that's the other one we have the 2 choices of how, if you want to subtract or if you want to be, clever. Yeah. Let me just draw a fresh bell graph here. Here's the curve. Again, here's the average. Here's 100. 122, and the reason why you want the labeling is it will help you position the figures quoted to you. 122 is a positive, and again, it would be, we're not worried about positives, but it's above 100, so the 122.5 would be here. If you're talking above that, we're really referring to the area that is just beyond it. So that barrier to the far right. All right. Now again, if you want to get this area, it would be equal to the total area, which is 1.0000 minus, all right, area from the left. So what would be the area from here to there, up to that point? So you could just look in the table at what this would be. Well, you get a calculator, which calls it a z-score first. All right. All right. So let's see. If your z is x minus x bar over that, 122.5 minus 100 would give you a difference of 22.5 over the standard deviation of 15. Right. Let's simplify that. We'll use our calculator. 22.5 divided by 15, you'd get 1.5. All right, so you have a z-score of 1.5. Now we're going to look that up in the table and put the area there. So it's a positive 1.5. Uh, 1.5 is 0.9332. So we would subtract 0.9332 from 1 whole. If you're doing this the more complicated way, we'll just put this back to get it less distracting. We'll take 1 minus that figure. 1 minus 0.9332. Okay, and you would get this naturally. 0.0668 for the area. Now, in terms of a percentage, that would be 6.68% of the total. Right? Again, that's the slightly more involved way of doing it. Means you know how to do everything. Cool. Right? With a little bit more trickery. Right? Once you have the z-score, we could just look up negative 1.5, and it should give us the same information. We should get 0.0668. So let's look at negative 1.5. And there you have it. Negative 1.5 is 0.0668. More than one way to do it, right? Cool. Okay. Let's look at this horseback riding problem because I think it's interesting. All right. It'd be a lot of the same technique, just applied to a specific scenario. Assume the length of time for a horseback ride on a trail at Triple R Ranch is normally distributed. Again, you see this phrase, draw this picture, draw a little ghost, X bar. Alright. With a mean of 3.2, so 3.2 hours in this case. Mean is 3.2 hours. And a standard deviation of 0.4 hours. Okay. What percent of horseback rides last at least 3.2 hours? All right, there's a couple of things here. Let's figure out where does 3.2 fit into this picture. The phrase "at least" is a little misleading, so be careful there. It's a little counterintuitive. When you see "at least," it means greater than or equal to. Right? So that's the minimum, right? Which means we'd be talking about this being the barrier. 3.2, coincidentally, it's the average, or better, which would be beyond this. That's the whole other half of the picture. Without doing a calculation, if you could reason it through and you've drawn the picture, we could say to ourselves, well, that would have to be 50%, right? Because that's half of the graph. It's 50% above the average. Okay. Now, next question. What percent of horseback rides last less than 2.8 hours? Now, in this case, if 3.2 is right smack in the middle, all right, 2.8 would have to be something on the left side of it. So in your picture, modify it like so. You're going to put 2.8 here. All right. And if it's less than that, then it's truly from the left then. All right. Now, what we would have to do in this situation is we can't just apply logic. We have to use the z-score formula. All right. So if z is the variable minus the average divided by the absolute value, all right, then you're going to take 2.8, substitute it, and 3.2, subtract, and then divide by 0.4, right, to establish a z-score. Okay. All right. So what's 2.8? Minus 3.2, it's negative 0.4 divided by 0.4, so you're going to get negative 1. Right. Now we need to look at this in the area table to get this to look at, convert it to a percentage. So we look at the table for negative 1 z-score, and we get 0.1587 right here. .1587, right, in the style of a percentage would be 15.87%. Okay. Let's see, anything else interesting here? Let's do C and then do E. If you look at C, it says what percent of horseback rides last at least again, there's that trick phrase there, 3.7 hours. Because I've got a lot of gobbledygook here, I'm going to erase a bit and modify my drawing again. I'm doing C, paying attention to at least as a suspect phrase. Here's a little diagram. 3.2 is the mean hours. The figure quoted to us in this is 3.7. So 3.7 would be here in relation to 3.2. And if it says at least, what does at least mean? It means greater than or equal to. Right. Which means, again, from above this line. This is the bare minimum. That's at least 3.7 hours or better. All right. So this is a situation where you have data that is coming from the right. Again, what we'll probably do, just for the sake of expediency, is we'll calculate a z-score. And then look up the opposite sign. You could subtract from 1 if you want, but this is faster. So 3.7 would be here, minus 3.2, and the standard deviation is 0.4 in this problem. So difference of 3.7 and 3.2 is 0.5 divided by 0.4, which is what? 0.5 divided by 0.4, 1.25. This is Z, 1.25. What we're going to do is we're going to look at negative 1.25, give that area, and then convert that to a percent. Right. So in the table, negative 1.2 is here. So that's 0, 1, 2, 3, 4, 5. 0.1056. All right. 0.1056, which is 10.56%. All right, that's the fastest way to do that. Okay. All right, one more of these and then I'll stop. All right. To answer E, which is getting a little cut off here, I'm going to have to scoop this up. I'm going to incorporate that information. Let's see. In a random sample of 500 horseback rides at the ranch, all right, how many last at least 3.7 hours? Well, we just got that information in the style of a percent. Remember, it's 10.56% of whatever the total is. All right. If the total happens to be a random sample of 500 horseback rides per se, all right, we can now just apply a percent equation, which is essentially 10.56% of 500. That means this as the decimal, 0.1056 times 500 is the answer. 0.1056 times 500, and you get 52.8. 52.8 rides. All right. Since you can't have, in normal circumstances, a fraction of a ride, really, round it. So 53 rides. And that's that. 53 rides will last greater than at least, or phrase prefers, it means the same thing, 3.7 hours. Okay. I think that's it. All right. Enough of that. Okay. For homework, I believe this is 2 parts. Do section 12.5. I believe it's part 1 and 2. For homework in my lab, and you're good to go. All right, I would definitely get on that because then there's section 12.6, which is pretty comprehensive. All right, you want to have a lot of practice in this before you get there. Okay. All right. Thank you guys for sticking with me. I'll see you again tomorrow. All right, be careful out there.